It's been over 50 years since the first humans walked on the surface of the moon. They kicked up dust, took some pictures, planted flags. Since then, dozens of missions have gone back. Some landing, some orbiting, others crashing on purpose just to see what might get thrown up. It's the most visited, most studied celestial body in space outside of Earth. And yet after all that, we still don't fully understand it. Not the way it stores heat, not the way it handles electricity, not even the way its soil clings to everything like it's alive. The deeper we look, the more questions we find. Some things like the way it pulls Earth's oceans or causes solar eclipses we figured out a long time ago. But other things, stranger things, have only gotten more confusing the closer we've looked. One of those things, it started with a signal, just a faint chemical trace, then another and another. Different missions, different methods, but they all pointed to the same surprising possibility. Something was there that shouldn't be, and what came next was a series of discoveries, experiments, and contradictions that would leave scientists scratching their heads for decades. It's easy to forget how slow science can be. You'd think that finding something unexpected would change everything immediately, but that's not how it works. Sometimes the most important clues are the ones nobody notices at first, or worse, the ones everyone notices, but no one believes. That's exactly what happened in 1976. The Soviet Union sent a robotic probe to the moon called Luna 24. It was the last mission of its kind, the final effort in a long series of sample return landers. It didn't make headlines. It wasn't the first of anything, or the biggest, or the most impressive, but it quietly did something important. It drilled about 2 meters beneath the surface, pulled out a small column of lunar soil, and sent it back to Earth. The total sample weighed around 170 grams. That's about the same as a baseball. Not much to work with, but enough to study. And inside that narrow tube of dust, something strange showed up, a trace of water. Roughly 0.1% of the sample contained H2O, and the deeper you looked in the sample, the more water you found. That should have been a big deal. It wasn't. Instead, scientists dismissed it. They said the water probably came from Earth. Contamination, maybe from the lander, maybe from the equipment back home. It was the easy explanation. After all, the moon was dry. Everybody knew that. The textbooks said so. This wasn't the first time something like that had happened either. Earlier during the Apollo missions, samples brought back by astronauts had shown similar signs. Not a lot, just trace amounts of hydrogen-bearing compounds. Some of it might have been hydroxyl, a close component of water, but again it was waved away, just interference, nothing serious. For decades, these signs sat in lab reports and footnotes. The data was archived. The idea was shelved. Nobody followed up on it. No one designed a mission to dig deeper or to test whether the water might actually be real. The assumption that it wasn't stayed in place, it wasn't until the late 1990s and early 2000s that these early signals started to look less like contamination and more like overlooked evidence. But by then, we'd spent years ignoring what was right in front of us. And by the time we were ready to go back and take another look, the moon had already started pushing back. If you stood at the edge of some craters near the moon's poles, you'd see something almost unnatural. Not because of what's there, but because of what's not. No light, not even a faint glow, just a sharp, permanent shadow that's never moved in billions of years. These regions are called permanently shadowed regions, or PSRS. They exist because the moon doesn't tilt much. Its axis is almost perfectly upright, only about 1.5 degrees off. That means when the sun shines across the poles, it skims across the surface almost sideways. And the deeper the crater, the easier it is for sunlight to miss it entirely. So there are places down there that haven't seen a single ray of light in almost the entire history of the solar system. That kind of environment is rare, not just cold, unchanging, no sunlight, no heating, no thermal cycling. The temperatures inside some of these PSRS can drop below minus 240 degrees Celsius. That's colder than Pluto, in fact, colder than anywhere we've measured, including the ice giants. These are places where theoretically ice could survive forever if it got there in the first place. That's what scientists started thinking in the 1990s. Maybe the moon wasn't completely dry. Maybe it was just keeping its water locked away in these cold traps. And if any water-bearing comets or asteroids had ever struck the surface, which we know they have, some of that material could have drifted into these shadowed basins, frozen solid, and never left. The idea caught on fast, not just because it made sense thermally, but because of what it implied. If the moon really had ice tucked away in deep frozen pockets, then it wasn't just a dead rock anymore. It could become a resource, a fuel depot, a place to build from, not just study. From that point on, the moon's polar regions became the new focus. It wasn't enough to look from afar anymore. We had to get closer. We had to see inside. But there was a problem. Those regions, the most promising ones, are also some of the hardest to reach. The terrain is jagged, the lighting is terrible, and you can't rely on solar power when the sun never rises. Still, the potential was too important to ignore. If there really was ice down there, it could change everything. So the missions started lining up one after the other, all with the same goal: find proof. And that's where things started to get strange again. Once scientists suspected there might be ice hidden in the shadows of the moon, the next logical step was to send something up there to check. But instead of landing, these early missions took the safer approach, orbiting from above and scanning the surface using remote instruments. The first was Clementine, a joint mission by NASA and the U.S. Department of Defense, launched in 1994. Its job wasn't originally to look for water, but it ended up making an important observation. Anyway, Clementine mapped large portions of the moon and revealed that some craters near the South Pole were permanently shadowed. That gave weight to the cold trap theory, but Clementine didn't carry the right instruments to confirm whether anything was actually frozen inside those shadows. A few years later, in 1998, NASA sent up Lunar Prospector. This time, the search for water was one of the mission's main goals. Using neutron spectroscopy, the spacecraft looked for signs of hydrogen, a potential indicator of water, or hydroxyl compounds, by measuring how particles bounced off the lunar surface. And it found something. Lunar Prospector detected high concentrations of hydrogen near both poles, especially around the permanently shadowed regions. It was exactly what scientists had hoped to see. On paper, this meant there could be anywhere from 10 million to 300 million metric tons of water ice spread out across the lunar poles. That's not a puddle. That's a global game changer. But there was a catch. Hydrogen alone doesn't confirm the presence of water. It could also be part of hydroxyl or locked up in minerals. The instrument couldn't tell the difference. It just said something was there, something containing hydrogen, but not whether that hydrogen was part of water ice or something else entirely. And even if it was water, the orbiters couldn't see it directly. They couldn't drill or touch or scoop. They could only suggest, not confirm. That left the science community in a frustrating position. We had data, we had strong hints, but we didn't have certainty. The moon was starting to show signs of giving up one of its secrets, but it still wasn't letting us get close enough to be sure. Orbiters gave us direction, but not answers. The maps lit up with potential. The shadows looked promising, but no one could say for certain what was hiding inside. That's when space agencies decided they needed a different kind of mission. If orbiters couldn't reach the ice, maybe a direct hit could. When orbiters couldn't give a clear answer, scientists tried something a little more aggressive. Crash something into the moon and watch what gets thrown into space. It sounds crude, but the logic behind it was simple. If the ice is buried in shadowed craters, and if orbiters can't see through that darkness, maybe smashing into it would toss some of the hidden material into sunlight. And once exposed, sensors could finally tell us what's really down there. The first major attempt came from NASA's Lunar Prospector. After completing its mapping mission, the spacecraft was intentionally steered into a crater near the moon's south pole in 1999. The hope was that the impact would eject a plume of debris high enough for Earth-based telescopes to analyze it and maybe catch a glimpse of water ice. But it didn't work. No water was detected, and the experiment was inconclusive. Some said the angle was wrong, others blamed the instruments. Either way, we learned little. Almost a decade later, Japan tried something similar with its Kaguya spacecraft. It orbited the moon for over a year, collecting high-resolution images and topographic data. And when its primary mission ended in 2009, it too was sent crashing into the moon again, with hopes that the ejector would reveal something hidden below. Once again, no useful data was recovered. No ice, no vapor, just dust. But then came LCSS, NASA's Lunar Crater Observation and Sensing Satellite, launched in 2009 with one clear mission: find out once and for all if there was water ice in a permanently shadowed crater. LCROSS didn't crash alone. It brought a companion, the empty upper stage of its rocket. That rocket body hit first, slamming into a crater called Kaguya near the South Pole. A few minutes later, LCROSS itself followed the same trajectory, flying directly through the plume of debris created by the impact. This time it worked. Onboard instruments detected water vapor in the plume. Not just a hint, real measurable water. Alongside it were other volatile substances: hydrogen, carbon monoxide, ammonia, methane. This was solid evidence. For the first time, a spacecraft had interacted directly with the lunar surface and confirmed the presence of water ice. The discovery made headlines. Scientists celebrated. The lunar South Pole was officially more than a theory. It was a target, and for a brief moment it felt like the mystery was solved. But then the questions started coming back. How much ice was really there? Was it mixed evenly in the soil, or locked in isolated pockets? Was it ancient or recent? And perhaps most importantly, could we actually use it? LCROSS had given us proof, but it was limited. The spacecraft was destroyed in the process. It couldn't explore. It couldn't follow up. And it couldn't confirm if what it saw was typical or rare. We knew there was water somewhere, at least in that one spot, but we still didn't know how much, how deep, or how accessible it really was. And that's when newer missions, smarter, slower, more deliberate, started looking for different answers. For a long time, the idea was simple. If there's water on the moon, it has to be in the coldest, darkest places. The permanently shadowed craters, the ones that never see sunlight, made the most sense. But then something unexpected showed up. Orbiters began picking up faint traces of water molecules outside those cold traps. Not in deep craters, not buried under soil, but right on the sunlit surface. It didn't make sense at first. NASA's Lunar Reconnaissance Orbiter had been mapping the moon since 2009. Its instruments weren't just looking at terrain. They were scanning temperatures, measuring light, and analyzing chemical signatures. One of its instruments, along with data from India's Chandrayaan, began detecting signs of hydroxyl and water molecules across the entire surface. Not everywhere and not in high concentrations, but widespread enough to catch attention. Even more surprising was how the signal changed over time. During the lunar day, especially around noon, when the surface was hottest, the water signals weakened or disappeared entirely. But as the surface cooled in the late afternoon and evening, the signals came back. It was as if the moon was sweating. Water molecules vanished during the heat of the day, then returned at night. Not as puddles, not even as frost, just a few scattered molecules clinging to the surface, or possibly shifting through the thin lunar exosphere. No one expected that. It's hard to overstate how unusual this is. The moon doesn't have an atmosphere. There's no pressure to hold water vapor, no weather to create cycles, no clouds, no rain. And yet the data suggested something like a lunar water cycle, not driven by evaporation or condensation like Earth, but by solar heating and cooling on a molecular scale. So where was it coming from? There are a few theories. One idea is that micrometeorites, tiny space rocks constantly hitting the surface, might be delivering small amounts of water or releasing it from minerals on impact. Another theory involves the solar wind. The sun constantly blasts the moon with charged hydrogen particles. When those particles hit oxygen-bearing minerals in the soil, they might create hydroxyl. And over time, some of that could turn into actual water. But no matter the source, one thing became clear. The moon wasn't completely dry, not even on the surface. And this changed the conversation again. Because if there's trace water almost everywhere, maybe we don't have to build a base right next to a frozen crater. Maybe the moon's surface is just wet enough to gather what we need. If we can figure out how that realization widened the map, suddenly more locations became viable, more landing sites, more potential for exploration. And that momentum carried forward into the next wave of missions. Landers and rovers designed not just to observe from orbit, but to land, drill, test, and confirm everything we thought we knew. And when one of those missions finally arrived at the moon's south pole, it brought with it new tools, new goals, and a big surprise. In 2023, India launched a mission that was supposed to be different. While many spacecraft had orbited the moon, mapped its terrain, or crashed into craters, Chandrayaan-3 was built to land, and to land somewhere specific. It was headed for the South Pole, the region scientists believed held the highest concentration of frozen water on the entire lunar surface. By this point, the reasoning felt solid. Multiple missions had detected hydrogen signatures. LCROSS had confirmed water vapor in a shadowed crater. The temperature data pointed to cold enough conditions to preserve ice. Everything added up. All that was left was to send something down there and finally see it up close. Chandrayaan-3 arrived in July. The lander named Vikram touched down successfully, making India the fourth country to land on the moon and the first to land near the lunar South Pole. Inside was a small rover called Kaguya, equipped with tools specifically designed to test the moon's surface and confirm what so many missions had suggested for years, that ice was there. Except it wasn't. The rover moved slowly, scanning the regolith with two instruments. One used lasers to break down surface material and read its chemical composition. The other used alpha particles and X-rays to do the same thing in a different way. These weren't estimates. They were direct in situ measurements, exactly the kind of hard data scientists had been waiting for. And yet, when the results came in, the findings were unexpected. The instruments picked up aluminum. They found iron, calcium, chromium, sulfur, even titanium. All good information, important for understanding the moon's geology and history. But one thing was missing: hydrogen. And without hydrogen, there's no water. The rover searched different areas. It stopped near craters. It examined untouched soil, but the data stayed the same. No water ice, no hydroxyl, nothing that matched the signals earlier missions had seen from orbit. That absence didn't make sense. This was supposed to be the moon's wettest region, the very place scientists had marked as the most promising. So why was it dry? Had something changed? Were we wrong about the earlier detections? Or was the water just deeper, out of reach of the rover's shallow tools? No one had a clear answer. The mission continued making other discoveries, taking temperature readings and testing the lander's ability to hop short distances. But as the lunar night approached, both the lander and the rover were powered down. They weren't built to survive the freezing temperatures of the 14-day lunar night, and after they went silent, they never woke up again. Chandrayaan-3 gave us a lot. It proved that India could land at the South Pole. It showed us new elements on the surface. It mapped terrain and measured heat. But it didn't solve the water mystery. If anything, it made it more confusing. Because if the water was supposed to be there, and every map, reading, and model said it was, then why couldn't we find it? That's when attention turned back to something that had been overlooked: the soil itself. Maybe it wasn't that the ice wasn't there. Maybe we just weren't looking deep enough. It's easy to think of the moon's surface as lifeless and simple. Gray dust, rocky terrain, no weather, no erosion. What you see is what you get. But Chandrayaan-3 quietly revealed something that challenged that idea. Not with what it found, but with what it felt. The Vikram lander was equipped with a temperature probe called CHASTI, short for Chandra's Surface Thermophysical Experiment. It was designed to do one thing: measure how heat moves through the lunar soil. It did this by slowly inserting a probe into the ground 1 centimeter at a time and recording the temperature at each level. On the surface, it measured around 60 degrees Celsius. Not unusual. The moon heats up quickly under direct sunlight, but just 8 centimeters down, the temperature had dropped to minus 10 degrees Celsius. That's a massive shift in such a short distance. And that sudden change told scientists something important. Lunar regolith is an excellent insulator. It doesn't transfer heat well. That means what's hot on the surface can stay cold underneath, and cold enough, just possibly to preserve water ice. This wasn't a theoretical model. It was a direct observation. The top few centimeters of dust act like a thermal blanket, allowing pockets of cooler temperatures to persist just below the heat. If there is water ice on the moon, And if it was buried just a little deeper than Prague's instruments could reach, it would stay invisible to surface-level scans while still showing up in the orbital data. That might explain why Chandrayaan-3 didn't detect anything. It wasn't wrong. It just wasn't equipped to dig far enough. And this matches other clues. Earlier Apollo and Luna missions had hinted that water content increased with depth. Spectrometers on orbiters picked up signals that couldn't be traced to the surface alone. Even the LCROSS plume came from below the upper layer of soil, kicked up by impact. So maybe we've been missing the obvious. Maybe we're brushing right past the ice. Not because it's hidden deep within mountains or frozen in rare pockets, but because it's sitting just beneath our feet, buried under a few centimeters of insulating dust. The problem then isn't that the moon is dry. The problem is that our tools haven't been sharp enough to dig properly. And if that's true, then the next lander won't need to fly further or see better. It'll just need a stronger drill. For decades, the search for lunar water was treated as a scientific curiosity, a way to better understand the moon's history, its geology, and the story of how water moves through the solar system. But that's no longer the main reason people are interested in it. Today, lunar water means something much more immediate: independence. Because if we can find usable water on the moon, enough to extract, purify, and store, it unlocks everything else. First, it makes long-term lunar missions possible. Water is heavy. Launching it from Earth is expensive. Every liter costs thousands of dollars to deliver. But if astronauts can source it locally, it reduces what they need to bring with them. That water could be used for drinking, cooking, cleaning, or cooling equipment, all without relying on constant resupply from Earth. Second, water can be split into hydrogen and oxygen, the same fuel mix used in many modern rockets. If we can build a system to extract water ice and convert it into propellant, the moon becomes more than a destination. It becomes a refueling station, a place where spacecraft can top up before heading deeper into space, to Mars, to asteroids, or beyond. That changes the math. Right now, every mission must carry all its fuel from the start, but a base on the moon with access to its own resources reduces the load. Launching from the moon is easier too. Gravity is just 1/16 of Earth's. That means less energy, less cost, and more flexibility. A spacecraft that launches from the moon doesn't need a giant rocket. It needs a push. Third, local water changes how we build. It can support closed-loop life support systems, recycling waste into usable resources. It can even help grow food. Some plants can grow in lunar soil under controlled conditions, but they still need water. If we find enough, future habitats might not rely entirely on supply drops or hydroponics. And finally, there's the geopolitical angle. Countries aren't racing to the moon just for the view. Water in this context is infrastructure. The first nation or company to control a usable, consistent source of lunar water won't just have bragging rights. They'll have leverage over access, over logistics, over where and how we build the future of space exploration. That's why the South Pole is getting crowded. That's why missions keep circling the same regions. And that's why every time we get close to confirming the ice is there and usable, the urgency picks up. This isn't about curiosity anymore. It's about capability. But even with all the interest, one thing remains painfully clear. We're still not sure how much water is actually available or how easy it will be to get. Because all of this, the fuel, the bases, the missions beyond the moon, only works if we can extract that water in the first place. And that brings us to the final problem. For all the missions, data, and optimism, the truth is we still don't have a clear picture. Every time it feels like we figured the moon out, it throws something new at us. A contradictory reading, a missing signature, an unexpected result. And this pattern has held over and over again. We've seen strong hydrogen signals from orbit, but no hydrogen in the soil when we land. We found signs of water vapor in impact plumes, but no frost, no ice sheets, no visible buildup. Even in craters that have never seen sunlight, places cold enough to keep ice frozen for billions of years, high-resolution cameras still haven't captured anything that clearly looks like ice. Instead, we get ambiguity. Shallow probes come up dry. Instruments detect water that seems to vanish during the day. Rovers drive past craters that should be full of frozen material, only to find more dust. Even new technologies like shadow cam, with its ability to image the darkest places on the moon, haven't yet revealed the kind of clear reflective ice patches scientists hoped for. It raises an uncomfortable question. What if we've been wrong about how the moon stores water? What if the models need revision? Or worse, what if the water is there, but so thinly spread, so deeply buried, or so chemically locked into the soil that we're not ready to access it yet? There's also the possibility that our tools, for all their precision, aren't quite good enough. Orbiters can't dig. Landers have shallow drills. Spectrometers can only read what light bounces back. And even then, interpretation is tricky. Hydrogen doesn't always mean water. Surface brightness doesn't always mean ice. And yet, despite the confusion, the interest hasn't slowed down. If anything, it's accelerating. More missions are being planned. More landers are being built. The South Pole is still the target, and the assumption is still the same. There's something valuable hiding there. We just haven't unlocked it yet. Maybe the next mission will bring better tools, a deeper drill, a working extraction system. Maybe it'll finally dig below that invisible threshold and pull up something cold and solid. Or maybe it'll just add to the list of strange results. Another reminder that the moon doesn't give away its answers easily. But one thing is certain. Whatever secrets the moon is keeping, they won't stay hidden forever. We've come too far and we're too close now. And if we do find what we're looking for, not just molecules, not just shadows, but actual usable water, it'll be the beginning of something much bigger than the moon itself. Because the moment we stop depending on Earth for everything is the moment space becomes open for good.